Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Almost everything today is blamed on climate change. Let's be fair. On one hand, you've got some, let's say, the left side of the table, who is, every time your children burp, it's because of climate change. There's always something to do with it gets too hot in the summertime. It's climate change. It rains too much. It's climate change. It snows too much. It's climate change. And on the other side of the spectrum, we have, let's say, the right-hand side. We have others who are making a living out of claiming that it's all natural in origin, and humanity has nothing to do with this situation. So what we're going to do here today is talk about some of the realities of climate change, what we do understand, what we really don't understand, and where the uncertainties are, in particular how they affect and may influence climate change and extreme weather events. Let's see if this works here for me. Because I want to start, as this is a classroom, I wanted to start with a quiz, of course. I hope you all studied. There you go. I would like you to take this quiz here. Which of these, in my class, you have to rank them. What is the most deadly weather phenomena on this list? And what would be second and third, etc.? How many would go for winter and cold, given this ugly day here? Oh yeah, oh yeah. How about floods? Oh, we got a good hail. Yeah, not much death from hail. Heat. Oh yeah. Hurricanes. Yeah, hurricanes are good. What else we got here? Lightning. Well, the answer, my friend, there you are. Heat by a long shot is the biggest killer in the United States. And this might be surprising. Tornadoes get all the press. Hurricanes get a lot of news for good reason. But over 10 years or so, it's always going to be heat. And so what we need to be concerned, we're thinking about the globe warming. How does that really affect the lives in the cities? How does it affect our lives in the future? And so heat has to be one of the issues that we talk about here. The evidence, you've seen this. I'm going to go through this quickly because I'm sure you're aware of this. We're changing fundamentally the chemistry of the atmosphere. All the greenhouse gases have been at some concentration for a long period of time. Here we're looking at carbon dioxide. It's been at 280 parts per billion for thousands of years until roughly 1800 or so, when we discovered how to burn things. And we got into burning things. And to be fair, we started burning things because it made our lives better. Much more improved technologies and such. And in response to that, you can see the carbon dioxide concentrations have been going up fairly exponentially. We're somewhere around 390 parts per million now, and best we can tell, the atmosphere hasn't been there in thousands and thousands of years. So we're conducting this amazing chemical experiment right now on our atmosphere. And the question is, what happens? Because we have no basis to go on here. How is the atmosphere going to respond to this insult? Temperatures seem to be increasing. You can see that there have been increases in temperatures. This is a global average temperature. You can see how the temperature has varied over time. It's certainly been back in the 1800s or so. It's a little bit cooler. Went through a warming trend between 1900 or so and 1940. 1940 to 1980 or so, it leveled off again and then started to rise. And since 1980, it's been on the rise. And something, if I remember my statistics, something like 6 of the 10 most hottest years in history have been in the last 10 years. So there is something apparently going on. The issue, of course, is that are we to blame, or is it just a natural oscillation? And so in the past few years, temperatures have been rising. And interestingly, the temperatures are not rising evenly. So the maximum temperatures at the top have certainly been going up. This is from 1950 through 2000. You can see a rise there. And the minimum temperatures have been going up even faster. And it's an important understanding here. We get our energy from the sun heats the ground then re-radiates energy back into the atmosphere as long wave, we call it long wave radiation, infrared radiation. There are selective absorbers in the atmosphere that collect that, warm the atmosphere, which then in turn re-radiates it back down to the ground. And it's that latter cycling from the ground to the atmosphere and back to the ground which really controls temperature on Earth. So when would we expect global warming to have its biggest impact? It's going to be at those times when the sun don't shine. And in those places that the sun don't shine, get your minds out of the gutter here. So nighttime is the time when the sun don't shine. Therefore, our canary in the cave is nighttime temperatures. Those will rise faster than daytime maximum temperatures. And we're seeing that on a global scale here. So the bottom graph shows the daily temperature range, DTR. And you can see that the daily temperature range is decreasing because the nighttime temperatures are rising faster than the daytime temperatures are. Where else don't the sun shine? Please be polite. The poles. And so the poles also are going to be a significant place for warming. Here we can see the trends in temperature. This is from 1901 to 2000 on the whole. You can see they're rising around the globe. The bigger the dot, the more temperature has risen. We can show here in steps from 1910 to 1945 there was an increase in temperature around the planet. And it seems to be the bigger dots are more in the polar regions. We hit that period between 1946 and 75 where there's sort of a mix here of warming and cooling going on. And then now in the most recent period here we have general warming everywhere, and the dots are getting bigger and bigger and everywhere, but with an emphasis on the polar regions. Interestingly, I had in my class, AOSS 102, extreme weather, you have to say it with an attitude, conduct a poll. I had them go ask their parents and loved ones in their hometowns their attitudes. Do you think the climate is warming? Do you think the climate is changing in your town? And here's the results. This is the first time we've seen these. This is hundreds of people asked around the state and elsewhere, and they can see that for the most part people think things are pretty consistent. There isn't a lot of change. So our perceptions are that we don't really see much change here, so they're all going to force us to say, well, where is this global warming? And more importantly, sitting in Michigan here on a day like this, you're going, well, global warming, yeah, bring it on. We all suffer, Houston. We want it warmer. So people aren't perceiving there to be big changes yet. This is interesting, the frequency of events. So here at heavy rains, do you think that there's more heavy rain now than there used to be? And it looks like a fairly normal distribution here. Most people don't really see a change in heavy rain. Windiness, people feel like it's getting windier. And they think there are fewer snowstorms. The perceptions, these are people's perceptions. We're going to go back and actually test where the answer came from and whether there's truth in what they're perceiving. But these are the sort of results we see from the public. And temperatures below zero, they see less of that. And temperatures above 90, they think that's decreased some too. So we're hearing from the people that the perception is that the climate is not really changing much in our hometowns. And that's what today's talk is about. On a global scale, I'm going to stand here and guarantee to you that the climate is warming. And for those people who want to take issue with that, bring it on. It would be silly for me to say otherwise. We can talk about how nature has its impact on that, but what I want to get down to today is how is it affecting my district? What's happening in my town, and how is the storms next week going to be affected by climate change? First of all, the models that are run by varieties of people around the country, Republicans, Democrats, French, whoever, run their models. And they run their models for the future, putting in the changes. First of all, I'm the first to admit that we're taking the same weather models, which are going to do a hard time predicting next week's weather. We're just going to run them for 100 years. And I'm asking you to trust me. But the difference in these models is we put in the radiative transfer. We put in the changes in the atmospheric chemistry. And that is going to influence then how energy gets stored in the atmosphere. And based on that, the models, you'll see that none of the models are predicting temperatures go down. And I show this in my classes, so the yellow is us people, or most of us in here. We're their parents. So here we are in the year 2000. So temperatures have risen by 2010, a fraction of a degree. But the the students in my class, our children, the you there, are going to be seeing far greater temperature changes globally. And then their children at the top are going to see apparently dramatic change. Now these are dramatic changes of 2 degrees centigrade, 3 degrees centigrade. So you might say, oh, whoop-de-doo. 3 degrees centigrade, it would be just fine if it didn't snow as much or whatever. Somehow, this is not a big worry to us, right? The problem is that this is not an equal opportunity global warming. It's going to affect different areas differently, and it's going to affect certain areas dramatically. And that's what the concerns are. As we said before, the temperatures are going to change where the sun don't shine. So models suggest, and each of these 3 rows here represents different estimates of different emission scenarios. How will we live? I love teaching global change at the University of Michigan or at any university because it requires that we talk between departments. So the science is the easy part, but we need to understand how are people going to change in response to this? How are political systems going to change in response to this? And this tries to capture from top to bottom different possibilities for how we as a people will change to this challenge. And in each case, it's showing that the temperature ranges there going out to 2090 to 2099, that decade. The temperature rises are going to be on the order of 6 to 7 degrees centigrade in the polar regions. And that's really bad luck, because that's where we keep the ice. And as we warm that area, there's a feedback mechanism that happens. So as you start to warm the Arctic region, what happens is you melt the ice, you start exposing water or land. That water and land can then absorb more sunlight, so it warms up even faster, and you have a feedback. And bad luck again, you start melting the permafrost. The permafrost has contained a lot of methane, which is bad luck, more greenhouse gas. So for all sorts of bad reasons, warming the polar regions is not good. And unfortunately, that's what appears is going to happen and is happening. So when we speak now let's get down to the day-to-day stuff, the good stuff here, the extreme weather. And I've broken it into 4 categories for today's talk: heat, hurricanes, floods, and tornadoes. And please understand, everything I'm about to say is totally speculative, but that's why I'm a professor. So I'm going to start with statistics, because what better way to wake up a crowd in the morning than a good talk on statistics. Typically, we have a normal distribution of temperatures in most cities around the world. And it says on certain days, in this case, I said the average temperature is 60 degrees. And there's a distribution of days, some very hot, some very cold, but they're very, very few in number on left and right here. So if we take that whole distribution of temperatures and just assume that the whole thing is going to shift and be warmer in the future. Take this distribution, and we're going to warm it up by a few degrees, that little red arrow top. Take the whole distribution and shift it to the right. Now, over here on the right side of the distribution, you see that little red blob. That represents the number of days when temperatures are ungodly hot, about higher than 95 degrees. And it's a relatively smallish number, right? If you shift that whole distribution to the right, what happens, that's cute. What happens is that you basically double the number of days where temperatures are greater than 95. Small shifts in the whole distribution make large changes in the tails, large changes in the number of extreme events. And this gives us pause. Some modeling studies show, for example, that right now I think it's Houston, Texas. I'm going to pick on Houston a lot today. In Houston, Texas, there's something like 30 days of the year where the temperature is greater than 95. Modeling studies suggest it's going to be like 90 days of the year in 100 years where temperatures will be above 95. Well, if you lived in Houston, why, I don't know. If you lived in Houston, well, how are you going to respond to that change in your environment? Chances are you're going to buy more air conditioning. You're going to do something to control your environment, which is going to require more energy, which puts more CO2 in the atmosphere, and then you have another positive feedback system going on. So this is how this system becomes so complicated and such a challenge for us teaching is it's more than science. How do people respond? How do religions respond? How do population changes happen in response to this? What happens to the disease? All sorts of interesting questions go on here. Speaking of heat, all right, we only have to go back a few years, the year of 2003. You may remember in France and Europe they had a heat wave that covered much of central France. The bright colors here are showing temperatures 10 degrees above normal. Happened in August in France and Italy. And in response to that, some 38,000 people died in that heat wave. We've had similar heat waves here in Chicago and in New York. And research suggests that these heat waves are going to happen. Now, a heat wave, I must define to you, is, yes, of course, it's a day with hot temperatures. But Phoenix has many hot temperatures, another city I puzzle about. Many days with hot temperatures, but there's a nighttime when it cools down and it gives your body time to sort of repair and adjust. But under these conditions of heat wave, what happens is it doesn't cool down at night. Let's go back a few slides. The sun don't shine. If we're keeping nighttime temperatures warmer, then we're bound to have periods of, maybe longer periods, more intense periods of heat wave. We cannot forecast yet how many or what will happen, but there are suggestions out there. Here are again forecasts for North America showing the changes in temperature from over 100 years between 1980 roughly to 2080. So let's start on the right side here. On the right side it says that the temperatures are going to rise, this is by 4 degrees centigrade, over much of the western United States. An area already known for its heat and dryness is going to get hotter and potentially drier in response to this in the summertime. But look at the left side. Now that's December, January, and February. The temperatures rise even more, especially up in the Hudson Bay and north going up towards the Arctic. Temperatures rising on the order of, what's that, 7 degrees or more centigrade. 12 degrees Fahrenheit rise in temperature. So there are dramatic changes happening, particularly in those times when the sun isn't shining, particularly at nighttime, particularly in the polar regions. And this has huge implications. I would like to bring that back and think about then how, okay, so the Arctic gets warmer, the tropics get a little warmer. How does that affect extreme weather? And that's what we're going to try to focus on here now. So here's estimates. Again, this is from this report, IPCC report, which tells us the increases in heat waves. And this might be a little surprising to you. They're suggesting that there's nowhere on the globe to be a decrease in heat waves. There'll be increases in heat waves everywhere, according to these modeling studies. And these modeling studies suggest that they're going to really increase, the pink, look at the pink areas here, really increase in places that are already pretty darn hot. So the Arabian Peninsula, the Sahara, and the western United States and Hudson's Bay suddenly has more heat waves. Well, again, these are weather models which are running out for long periods of time. So again, there is uncertainty in this, but when we say there's uncertainty in this, understand the uncertainty could go either way. We could be overestimating or we could be underestimating. This is the best physics we can come up with, the best models representing that physics, and based on this we have sort of the best guess we can make. We all have to make forecasts for the future, and this is, yes, there's uncertainty, but understand that it can go both ways. We could be underestimating. Dry days, the number of dry days forecast for the future increases almost everywhere. And notice particularly Europe hits some increase in dry days. The Mediterranean has more dry days. The southwest United States, more dry days, if this is true. Things will change. Temperatures get warmer here. You have winter times being less cold. That's not necessarily bad for us unless creatures who we don't know about, little bugs, live longer in the wintertime. We have more mosquitoes or something. All sorts of things may happen. Responses are outside my field. But there are going to be responses to this. So heat is sort of the easy one. We expect temperatures to rise globally. We expect temperatures to rise really a lot in the polar regions. We expect that to have ramifications for how that area responds. The second topic to talk about today is hurricanes. And to do that, I have to explain to you the energy which drives a hurricane. We get a lot of sunshine in the tropics, right? And we get a lot less sunshine in the polar regions. And so what the Earth has to do is it has to distribute that heat. It has to move that heat around. There's excess heat in the tropics. And the way it does that is through transport of energy out of the tropics to the polar regions. That's the weather engine. This movement of heat from the tropics to the polar regions is what drives virtually all storms. But what better way to take a lot of energy out of the tropics and throw it into the polar regions in a hurry than the hurricane? What a great design that is. We move a lot of energy in a short period of time out of the tropics. But the way a hurricane works is far different than the storms which we know and love here in Michigan, which I'll talk about in a moment. Hurricanes are entirely based on the evaporation of water. You must evaporate water from the surface of the ocean. It takes 600 calories to evaporate a gram of water. You pick it up now as invisible water vapor, transport it to somewhere like Michigan, where it now creates a cloud. Where it creates the cloud, it releases that heat, 600 calories per gram. So what you've done is effectively taken energy in the tropics and moved it to where the clouds form farther away. A hurricane runs on this. A hurricane takes that evaporated water, and the condensation that occurs inside the hurricane. Oh, this reminds me to talk about this. So you need water vapor, and you need the water vapor to converge. So out in the middle of the ocean, you have to have air converging together, forming the air, causing the air to lift up. As it lifts up, it condenses, and that condensation releases heat, so the inside of the cloud winds up being warmer than the outside of the cloud. And that produces a buoyancy. And that's the entire thing that runs in a hurricane. You do need the Coriolis Force. And if you've forgotten what the Coriolis Force is, it's simply that the Earth is turning beneath us. It is not the thing that makes your toilet go one way or the other. Those are other forces we won't talk about. This is all about how the Earth turns beneath us, and if air is moving for long enough, then the Earth moving between us will cause the air to appear to turn to its right in the northern hemisphere. This is the Coriolis Force. You need that. And you need a little wind shear. So as that column of air is rising, it has to rise pretty much through the same column. So the next air that comes is going to follow the first column up, and it has sort of recurring bubbles of air. If you have too much wind shear, then the air rising is going to get torn off and blown away, and you don't have any organization in the storm. So you have to have a little bit of wind shear, but not a lot. And do not add water. This is a sort of recipe here. Do not add land. Once you add land, you've cut off the source of moisture, the hurricane dies. So here are the paths of almost all the hurricanes for the past 50 years. What do you see there? Or what don't you see there? Nothing at the equator. Thank you very much. And not much on land. So you have to have the Coriolis Force. The Coriolis Force is 0 at the equator. You cannot get a hurricane at the equator. You have to get 5 degrees or so away from the equator before you get sufficient Coriolis Force to cause the rotation to organize the storm to make it grow. Most of these storms will move from east to west, you see, until they get to a certain latitude and then get pulled back to the right, and that has more to do with the general circulation of the atmosphere. So the question I put to you, given what I just told you, is how could climate change then impact a hurricane? Why would we worry? What's the worry? Well, we would have more heat. That's true, except the polar regions are going to get plenty more heat themselves. So the imbalance might actually be a little bit less. You need water evaporation. And what's the one thing that controls the rate of water evaporation? Temperature of the oceans. So if you warm up the atmosphere, invariably you're going to warm up the oceans. You warm up the oceans, you're going to have more evaporation of water. Consequently, you're going to have more potential for hurricane or tropical storm formation. So, we're very interested in how temperatures of the oceans are changing in response to the atmospheric warming. And this is just a side view to remind me of this process in the hurricanes where the oceans are the source of the moisture, the rising air causes these hot towers that are the organizing force behind a hurricane. So if we warm the oceans, in theory, we should get the potential for more tropical storms. Well, here are temperatures around the world. You can see, as you might expect, that the warmest temperatures are in the tropics. You can see some variations on that off the coast of Peru, off the west coast of South America. There are the colder area there of water. That's unique in that there's an ocean circulation going on there. That's a whole other talk. That ocean circulation causes an upwelling of cold water off the coast of South America, which leads to something we call El Nino. That's a separate thing. But for the most part, it's warmer in the tropics and colder in the polar regions. This is the area, and what happens also, we know that if the water temperature gets less than 79 degrees Fahrenheit, you don't get a hurricane. It's like cutoff point. So if you can increase the size of the area that has that criteria of 79 degrees, or warm the existing area up more, then you're increasing the potential area for hurricane formation, and consequently, potentially, the size, intensity, or longevity of a tropical storm. Moving around the globe, you can see this is fairly common. Hurricanes happen almost everywhere. They're called different things in different parts of the globe. Typhoons, cyclones, willies around the globe. But they're all the same physics. And they all will run on the fact that water is warm. So we're warming up the globe. We're going to warm up the water. Are we warming up the water? Well, here's some data showing in various, first the upper left-hand corner here shows basically the world's oceans, how their temperature is changing. And if you stare at that long enough, you can maybe convince yourself that it looks like the temperatures are in fact increasing in the oceans over time, particularly since 1980, much like we saw for the atmosphere. We can go to each particular, the northern hemisphere, the southern hemisphere here, and we can see changes then in temperature which are occurring in these areas of the world. And based on that, there's some new data out from Kerry Emanuel and others around who have done some studies on this, indicating that in response, what they've done is they've gone back and studied every hurricane for the last 50 years and basically calculated the power. We call it the power of the hurricane, which it has to do with the wind speeds and the size of the hurricane. How much energy basically is that hurricane creating? And quantifying the energy per hurricane, then looking over time to see how that energy has been changing. He published this in Nature a few years ago, and it shows what looks like an increase then in the amount of energy, total energy in hurricanes over time. This is, understand it's a difficult calculation. Nonetheless, there is evidence here, and he has more sense showing us that the hurricanes likely are increasing. We see that the temperatures in each of the ocean basins seem to be increasing. I'll walk you through these. The top one is the North Indian Ocean, the Western Pacific Ocean, the South Pacific, Southern Indian Ocean, North Atlantic, for example. Temperatures, if you stare at it again, the North Indian Ocean, there seems to be a trend there. And there seems to be a trend in the North Atlantic. It could be a trend in many of the ocean basins. We think there is. In fact, the oceans seem to be warming up faster than our models suggest they should be, which gives us some more pause. Again, that uncertainty we could be underestimating. So the oceans are warming. Webster from Georgia Tech gives us this data where he's looked at the number and types of hurricanes over time. And it suggests that, well, maybe the category ones, remember the hurricanes are in category 1 through category 5. Just as an aside, I love this concept that science is a contact sport. And I'm going to show you in a few minutes here, when we're talking about tornadoes, how I love to take students out in the field. And you all remember that show, Wild Kingdom? where the guy sits in the van, and I'll sit in the van while Jim goes out to wrestle the alligator. I'm the guy in the van sending the students out, well, get closer to that tornado, you know. I love doing that, and anytime I can take students and put them in a life and death situation, they learn. Or they die, which makes grading a lot easier. So one of the things I've done in the past few years, and we'll probably do again this year, so students are here, hear this, is I have a competition which comes up in March where we take the 64 teams in the NCAA tournament, and basketball tournament, and we list those schools. Now the students test, and anyone here can play along, by the way. It's this place called weatherdance.org. Anyone can play along, and you have to then take those teams, you estimate which of the two teams' campus is going to be warmer on game day. And then that team advances. It's nothing to do with basketball after the first round. And it goes on with colder, warmer, and then there's winners, of course. And we offer a prize that the 2 or 3 students who do best in my class, I take them up to North Campus. You may not know we have a wind tunnel out there. So I take the winners and stick them in the wind tunnel, and we turn it up to hurricane force. And I stand outside pretending I can't hear them. It's really hard to breathe at 75 miles an hour. It gets even harder at 90 miles an hour, as these students will learn. So I tell you that because on this graph it shows various categories of hurricanes. Category 1 is sort of entry-level hurricane, where winds are like 75 miles an hour, 75 to 90. So the students will never see anything above Category 1. Still, it's hard to stand up, really hard to breathe when you're in that environment. But what we're seeing is not so much an increase in those entry-level hurricanes, but we're seeing an increase in the number of massive hurricanes, the Category 4 and Category 5. And so is this the response? Are we seeing a response to the fact that the oceans are warmer and these storms can last longer and over more space, they have greater fetch, maybe they're gaining more energy? This is an area of research in question. But there is the possibility here that we would see an increase then in tropical storms in response to global ocean temperatures. Floods. That's downtown Iowa City not too long ago. Floods, would we expect more floods in the future? I'm going to give you something very confusing and tell you up front the punchline. Is models suggest that we will have more heavy precipitation events and more drought. The models suggest that, let me just go there. To understand a flood, we must understand first the process which creates the storm systems which create the flood. The process that creates those storm systems, this is different now than hurricanes. This is going to be all due to dynamics of the upper atmosphere and linked to the jet stream. So basically here we have a map from Georgia going up through Indiana and the state to the right that I can't mention. And it's warmer in the south and colder in the north. We know that much. And so in response to that, basic laws of physics tell us that the area that's warmer, air expands. It rises and well, it gets taller. And where it's colder, it's going to stay more compressed. And so if we're looking at a particular height in the atmosphere, say halfway through the atmosphere, you have to go higher over the warm area than you do over the cold area. Does that make sense? You expand the air. In response to that air, then even though the pressure at the ground will be the same in the north and the south, if there is no change in pressure, there is no wind. But by simply warming the south and cooling the north, it causes the air to rise in the south, causing a pressure differential in the upper atmosphere from south to north. Therefore, air wants to move naturally from south to north. And would do that were not for the Coriolis Force. So as the air tries to march from left to right in this diagram, it's going to be pulled to its right by the Coriolis Force and wind up blowing from the west. Ergo, our storms come from the west because it's warm in the south and cold in the north. Now, that's part of the story. So we expect a west wind because of this simple law of physics. Now, on a particular day, and here's a situation, let's say you take these cities going from Miami through a place they drive large cars in Georgia to Asheville, Cincinnati, Detroit, and Sault Ste. Marie. And think about the temperatures across that, along that line. And here's a diagram where I'm saying that in Miami it's 55 degrees, in Sault Ste. Marie it's 55 degrees. In fact, I've made it 55 degrees everywhere in this diagram. In that case, the air over each of these cities would have expanded in equal amount. And therefore, the pressure fields above it would all be flat. So if the temperature didn't change from south to north, there'd be no wind. And I show you that to show you this one. In this case, it's 80 degrees in Miami, and it decreases quite linearly to Sault Ste. Marie at 30 degrees. What do you expect now to happen? You know, the slopes are going to happen, and the slopes are actually going to increase with altitude. So by warming the south and cooling the north, we would create wind, and the wind will increase with altitude because the slope becomes greater with altitude in the pressure field. That's why you fly jets high up in the sky, because that's where the winds are strongest. All right? Now take the more realistic case. This time we have winds, it's 80 in Miami, it's 80 in Savannah, Georgia, 75 in Asheville, dropping to 40 in Cincinnati, which is not uncommon. We have a demarcation here between warm and cold. In this case, looking at these pressure fields, they're going to change with altitude, and they're going to change more dramatically with altitude, and they're going to be most dramatic over that place where the temperature changes the fastest, between Cincinnati and Asheville in my model. So that's the place where the wind speeds will be highest and wherever the slope is the greatest, which is going to be high above the place here between Cincinnati and Asheville at the top of the map. That's the jet stream. The jet stream happens over the place where temperature contrast is greatest at the ground. And the jet stream becomes the instigator of most storms in North America. The jet stream carries with it the potential for what we call convergence and divergence. So the divergence, which happens with this, the air is moving along and suddenly moves faster in one spot. Air has to rise up to fill the void, and that causes an uplift and causes the pressure to drop at the surface, and that's how these storms like we had last week in Washington. Oh, Fox News. They claim, by the way, that global warming is over because we've had 2 snowstorms in Washington. Please. Don't get me going. Sorry. What I was trying to say was that these storms, these large storms such as we had in Washington, occur because there is a large temperature contrast at the ground. You have warm air to the south, you have cold air to the north. That produces a jet stream aloft. The jet stream aloft produces divergence, sucking the air out of that column, making the pressure at the ground become lower, causing the temperature contrast to get greater, and this becomes a cyclical process of cyclogenesis, the formation of storms. So if there is going to be global warming, how would that affect this system? How would we expect then this pattern I've just talked about where temperature contrasts have to be greatest to change? That's an area of open research right now. And I can't tell you we have a good answer. But there does suggest, and again, these large modeling studies, that the amounts of precipitation are going to increase. They're going to increase, but they're going to increase largely in the northern climes, in northern Canada, in northern Europe. Increases in precipitation. And we expect that increase in precipitation to be fairly dramatic over much of the globe. But here's the thing. The models also tell us that these precipitation events, there are going to be more precipitation occurring in fewer events. This is a surprise. More precipitation in fewer events. Therefore, you have more periods without rain, but when you do get it, holy cow, you get some dandies. And so in terms of extreme weather, you know, we're out on speculation and limb here now, I guarantee it. But this is the best models we have, and they are predicting that the kinds of storms we get in the future would, first of all, move further north, in response to the shifting location of the jet stream, and also would be more intense when they do occur. Here's what you've been waiting for. Tornadoes. Now, when we talk about tornadoes, again, how do you create a good tornado? First of all, you must have what we call convective instability. The atmosphere has to have certain thermodynamic characteristics to have a tornadic storm. Second, you must have what we call wind shear. That is, wind at one level has to be moving one direction, while wind at the other is moving in a different direction. You must have wind shear. And lastly, you have to have a trigger mechanism. The first two sort of give you the fuel. The last one sets it off. Let's talk about convective instability in a word here. What it says is if you have air at the bottom of the atmosphere here, and that's representing temperature, which is changing very little between 1,000 and 900 millibars. And we're going to lift that layer somehow. And the top of the layer is dry, and the bottom of the layer is saturated, or foggy, let's say. Then the bottom of the layer is going to cool at what we call the moist adiabatic lapse rate at 6 degrees per kilometer. It must. By theory, it must. And the top of the layer is going to cool at the dry adiabatic lapse rate of 10 degrees per kilometer. And so what happens here is that you systematically make that lapse rate, that red line, become steeper as it rises, which says that if somehow you can take this convectively unstable layer here, which is moist, a layer of moist air near the ground and dry air above it, and somehow lift it, that it will actually become less stable as it rises. It exacerbates the problem once you begin it. I've taken many students out chasing tornadoes. I've taken my own daughters out chasing tornadoes, much to the chagrin of my wife here. And they sat out in this field, and if you've ever been to Dodge City in the middle of the summertime, it's not a tourist attraction. It is one of the biggest meat packing areas in the world, and it stinks to high heaven. And they were complaining and grousing about this. And we drove for hours out in the middle of nowhere, and suddenly this little puffy white cloud formed, and people are pretty much jumping up and down, and my daughters are going, what? We drove this far, and that stinked. We'll see that cloud. And those of you who are parents can appreciate that the words are actually stronger. But as we followed this cloud, and the storm exploded. I mean, within 20 minutes, it had become some 10 miles tall, 40 miles across, growling black on the bottom, green on the bottom, with lightning everywhere. And the same two daughters, one of them's leaning out the back window with a big camera, and the other one's in the front seat with a walkie-talkie, breaker, we're coming through. It's a sight to behold. It's like visiting a national park that is only there for about an hour, and you get to see it all. And I'm going to show you some video in a moment of what the good and the bad news there. Anyway, so here to create a tornado, you must have this convective instability, and so that's step one. Step two, you must have this wind shear, where you got winds from the southeast at the ground, winds from the west aloft, and it produces this rotation, you see. And that rotation can then, if you can somehow lift that layer up, it's going to carry with it the memory of that rotation into the cloud. And you have now two rotating columns, one rotating counterclockwise, one clockwise. Again, by the Coriolis force, the one rotating clockwise is going to die out because it's moving in direction opposite the Coriolis force. But the other one is going to be intensified, the one rotating counterclockwise. That can become the tornado. Therefore, when you chase tornadoes, you don't just chase any cloud. First of all, step one, you want to be the chaser, not the chasee. That's very important. And to do that, you want to be in the right part of the cloud. So because of these dynamics, you want to be on the southwest side of the cloud. That's where most tornadoes form, on the southwest side. In fact, I think I have a diagram. Here we go. So the idea is you know where these clouds are going to form. You're going to drive behind them and follow them, watching behind you all the time. But you're going to follow these things in this place we call the rain-free zone. This is the part of the cloud now which is rotating. You can visually see these clouds rotating. We take our cars out, we park underneath large power lines, which may not make intuitive sense to you. But large power lines have on top of them large grounding wires. And our biggest fear is lightning. So we're standing under the power lines, the lightning will strike the power lines, and as long as they don't get knocked them down, You're actually safer under the power lines than you are outside the power lines. So we do many things to avoid lightning, but you want to be in a position here to film this. And once the tornado forms, it's going to come out of what they call the wall cloud here, right in the middle of this storm. What you don't want to do is be driving through this cloud on the rainy side, because then you drive out into this rain-free zone. You usually have like a 10-second moment where you have to make a life decision. And if you're not standing at a crossroads at that moment, it's not pretty. So in order to make tornadoes, you have to have these 3 ingredients. I didn't talk about the trigger yet. So first of all, you have to have moisture. And usually we have lots of moisture coming out of the Gulf of Mexico. Maritime tropical air traveling up into the Great Plains states, Oklahoma, Kansas, and such. And aloft above that, we have winds coming across the Rockies from the west, which produces the wind shear. So we've got the convective instability and we've got the wind shear in this situation, but we don't have the trigger. The trigger winds up being something else. And I've asked my students the same question I'll ask you. If you had to guess, which is heavier? 90-degree air, which is bone dry, or 90-degree air, which is muggy? How many say muggy? Yeah. How many say dry? Okay, dry winds. Basic chemistry. Go through and take nitrogen molecules and oxygen molecules. They each have a molecular weight. And now you're going to put in water vapor instead. Water vapor is lighter than nitrogen or oxygen. So if you start mixing in water vapor, it winds up that the air becomes lighter. So what we're looking for is hot, dry air. This initiates the tornadoes. So we get dry air coming out of West Texas, New Mexico, something called a dry line, moving into this area of the world. Then that produces, it's like a wedge moving across the countryside. And so I send these same students out in their vehicles to measure how does the dew point change across this area. And you can find that spot where the dew point suddenly drops dramatically. That's where you sit. Because that's the place, that's the wedge that's going to produce that, it's going to give it enough energy to punch through that upper layer and cause the air to start to rise like my daughter's experienced. So you need these 3 ingredients. Anything here that would be changed due to climate change, due to global warming? Well, certainly the maritime, there might be a little more maritime tropical air, but we have plenty of moisture now, so I'm not so convinced that's an issue. The winds aloft, well, it's possible that the jet stream will shift further north for reasons we've discussed. So maybe the locations of the tornadoes gets further north, but you still need that trigger, which is going to come from the southwest. And, well, okay, the southwest might get drier and hotter. So it's possible there'll be a shift in tornadoes to the north and they could become more intense. But now that's really speculative, so I'm wary of that. If we look at the number of tornadoes, though, over the past 50 years, 60 years, you probably see a trend here. The number of reported tornadoes has gone up. Is it global warming? Probably not. In this case, this is reported tornadoes. And what's happened over the same time is not only has the climate been changing, but technology has been changing. And we have more people with camcorders and more people living in places that they weren't living before who are able to report this. And our radar now is able to detect tornadoes that people don't even see. Doppler radar tells us where a tornado is happening. It's sort of a Zen question. If a tornado happens in the middle of Kansas and no one's there, does it matter? You know, just this sighting criteria for the next trailer park, I guess. So these data, scientists don't think this really represents an increase in the total number of tornadoes, but more just an increase in our availability to report tornadoes. All right, now we're at the end here. I wanted to share with you, though, I do take the students out into the field. This is 4 years now I've been doing this. And it's an experience that you don't quickly forget. First of all, please understand, anybody who wants to go tornado chasing with us, you cannot. You have to, unless you're a major in our department, then you're invited your junior year to get thrown in the path of a live tornado. So what we do take out, when we do take you into the field, you have this summer we had some 50 vehicles. We had 4 tractor trailers with radar on the back. We had more computers in these vehicles than most small colleges. We have download links. this is funny, but we are driving through the countryside out there, and when we need to get an update, we circle hotels. And God bless the people who are trying to watch cable news or something inside. Because we just suck the contents out of these buildings by taking the free Wi-Fi and taking whatever we can. Leaving the hotel people wilted. And so we have a great deal of information. Plus we have satellite downlinks. We have all this information. Nonetheless, even with all this science, and you should never, ever go tornado chasing unless you have this sort of information with you. Even with this, you put yourself often in dangerous situations, as I'm about to show you. So I'm going to share with you what I call the bad art of chasing tornadoes. And an example comes from 2 years ago in a town called Oberlin, Kansas. Let me set it up this way. This is Oberlin, Kansas, a metropolitan area here in the upper left-hand corner of northwest Kansas. Now, we had 3 University of Michigan vehicles in the field, and as you'll see in the video in a moment, and I'm going to apologize right now if you have children in the room, some parts of the video I'm about to show you are a little more animated than I would hope for, but I apologize. But nonetheless, so you're going to see videos from 2 of these vehicles, and what happened in this case is we're sitting here, we knew a storm had formed to our south in an area about there. And we also knew that these storms are moving straight north this day. So we knew that the storm had the potential to create a tornado, and we were having a debate, which you'll hear some of this debate on the video. We're having a debate about whether we should stay here or move, and to make our observations. Now, our goal was this. We're waiting for a tornado to form. We want to be the chaser, so we want to be behind the storm, following it, so we can drive behind it and take measurements of the inflow and various thermodynamic characteristics. That was the theory. Things went badly this day. So here's our 3 vehicles. The storm forms, it's moving north, and it's moving north at a fast clip, 50 to 60 miles an hour. So basically we have 30 seconds to make one of those big decisions. So each of the vehicles responded in a different way, and I'm going to just walk you through this once or twice here so you can watch the 3 vehicles and how they responded to this storm. I'm going to show you now a video from the first to the car on the right, and then second from the car on the left, and I'll tell you the story about the 3rd car that I was in the middle.
Okay, we are at west 100 degrees, 21.2168. Holy smokes. Look at this precip wrapping in. You guys seeing the rotation in the precip and cloud field here?
Rotation on the
T1?
precip is usually a good sign to get your tail out.
Yeah, go ahead. What you got?
We have precip rapidly moving westward while the base of the cloud rapidly moves eastward.
Oh, that's a tornado.
Okay, we got a tornado
That
on the
is a
ground
tornado.
directly to our south. We may need to move east here. This is very close, guys. You may want to move east also.
Here, Matt, grab the camera. Let me know when you want me to go. Oh, and then stop again. I think that's the first thing that we saw.
Now watch this tornado grow. It's a large tornado. It's going to have multiple vortices in it, which tells you it means some serious business.
Real close to them.
They lived. Vehicle to the west now.
Okay, we got a
Tornado found it.
Yeah, directly to our south. We may need to move east here. This is very close, guys. You may want to move east also.
We're on it. We're on it. Perry, move east. Get east, Perry. Get east. I hear it.
Alright, let's go.
Go.
Let's go, Joe.
Joe. Go.
Now they're arguing with the driver
feel
to move
safe,
away from the tornado.
Stand by 1 second, guys. We're going to get judge
Joe
distance on this
opts
thing.
not to.
Get the computer down to your lap. I can't see.
You better get.
Get out of here.
No.
Crap, dude.
I'm staying put. Windows up. Windows up.
This car coming.
Multiple vortices. An outrageous tornado of F3 or bigger. Now, the third vehicle I was in, and you saw in the animation, was in between these two. And what happened was I was trying to follow the first vehicle, and the rain got so intense that I could not see from me to the front of the car anymore. The rain was so intense, and debris was now flying against the car. And at that point, I turned the car. The only thing I could think to do was turn the car straight across the highway into the wind, and to try to take advantage of the aerodynamic properties of the vehicle. By the way, I'm now going to do a plug for the Chevrolet Cobalt. Aerodynamically, one of the best damn cars in America. So debris is hitting the front windshield, and it's like you saw in Twister, where fortunately that field was fairly open. So straw is striking the front window, branches are striking the front, and vibrating on the front window, and then blowing away, and something else is coming. I'm waiting for the cow, you know. All this debris, and finally, and all I can see out the window is a stripe on the road, because everything else, it's so dark inside you can't see anything. The car gets not picked up, but let's say bounced across the highway a few times, and all I'm thinking is, well, get in a low position, because if the car is going to go over, I will try to maximize my potential to survive. And as it turned out, the tornado passed, probably some 100 feet or so away from me. I didn't see it. I tried to take a picture. My sister, by the way, my brother are both meteorologists also, and we have a pact that if one of us dies prematurely, the others get rights to the last photo. So I was trying to do my job and take the photo, but it was so dark the camera wouldn't click, and so I just held on for dear life. And after the storm had passed, I got out of the car, and it was remarkable in that the car's wheel wells were totally plugged with soil. Totally plugged with soil. And maybe more remarkably, there was straw embedded in the side of the car. Everywhere there was a crack between the door and the window, straw stuck straight out of the car. This is showing the change in pressure and wind speed. Now, normally for winds to happen, say a very windy day in Ann Arbor would be caused by a change of maybe 4 millibars between here and Kalamazoo. That would cause a pretty high wind in Ann Arbor. So what we're seeing here is the pressure changed by 15 millibars in a matter of roughly 20 seconds. And in response to that, the wind speeds at that one car exceeded 130 miles an hour. The other car measured also winds in excess of 130 miles an hour. So we estimate the car I was in was probably seeing winds closer to 200 miles an hour. Cobalt. And when I returned that to the rental shop, they asked if how do I like the car? Oh, it's good. Thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.